So here we go. This is probably in your homework. Your homework will be due Tuesday because your test is on Wednesday. Test sheet? Wednesday. I don't think there's a blue sheet for this.
Yes.
So what we're going to do is we're going to do this math problem, and then we're going to graph it and use this to talk. So I'll help you with the first part and the process, but then you have to do the rest. Are we ready? So what this is, it says you have a 20 milliliter sample of 0.2 molar HBr solution. You would remember that that's the acid, right? It's titrated with 0.2 molar NaOH solution. Now, what does titration mean? That means we're dripping it in, we're adding it, right? It says calculate the pH of the solution after the following volumes of base have been added. So A is 15 milliliters. So what you have your 20 milliliters of acid, and it's 0.2 molar. And then in part A, we add 15 milliliters of base, and I'm just going to put, OH minus. You okay with that? Yeah, because it's just not really part of this acid-base thing. You AP math people are kind of a pain.
It's already too late.
All right. So what we would do now, and you'll do it each time, is you're going to calculate the amount of acid that we have. So we would take our 20 milliliters, because when I say amount, I mean the moles of acid that we have. So we take 0.02 liters, because whenever I'm doing molarity, it's moles per liter, right? And then I multiply that by 0.2 moles per liter, and you end up with the number we're going to use every single time, which is 0.004 moles of H plus. Okay? Now, every time we do one of these problems, this is the acid, and we're going to see how much of it is neutralized, and then find out what's left over. So what we would do, I should have written here, 15 milliliters of 0.2 molar OH. So for part A, you calculate the moles of base, which is just 0.015 times 0.2, and that's 0.003. The next thing you would do is you would find excess. So which one is in excess, this or this? The bigger number, the red one. That's my acid. So I take my acid, 0.004, I subtract my base, 0.003, and what do I get? 0.001. Now that's moles of H plus, correct? Now I can't get pH yet. I have to do one more thing before I can solve for pH. All right, divide by 0.035. Does anyone know where Smithers got that?
Liters.
All right, it's the 20 milliliters plus the 15 milliliters we put in. So 0.035, is that what you said? Yeah. And that gives you a number, 0.028. Let me summarize real quick. So first we found the moles of base, then we find the moles of excess, then we divide by new volume. Which is that number. And then this gives us the molarity of, which was in excess, H plus or OH minus?
H plus.
Of H plus. And what do you do with that now?
Take the negative log.
All right, so then you take the negative log of H plus, and that would give you your pH. So the negative log of 0.028 was 1.7 last hour, or 1.6. 1.54. 1.54?
I got 1.55. I got 1.55.
Well, okay, we'll just say 0.55. Now, just briefly, if your excess is OH minus, there's one more step. Do you remember what that step is? Subtract this answer from 14. Okay, so this is part A. What I would like you to do is the same idea for part B, C, D, and E, and then we'll get good at the math, and then we'll plot it, and we'll get good at the concepts as well. So what we've done there, I've taken the answers and I've plotted them on a graph for pH versus milliliters added. And this curve looks like what type of curve? What would we call this? No, it's called a titration curve. It's okay. I'm sure all of you read it, but you've just forgotten. Right? All right. This would be a nice smooth titration curve. This is what they look like. They have three main parts that we'll talk about. But yes, we can do another one of the maths. Part C was asked. Part C is actually the easiest, but that's okay. Do you remember we had, for acid, we had 0.004 to start with? When we do the math with 20 milliliters times 0.2 base, we end up with 0.004 OH minus. And what's the difference equal to?
So you do 0.02
Zero.
times by 0.2.
Uh-huh. Now, if there is no excess H plus or a OH minus, then we would say they're equal, and we would call that pH neutral, which is 7. Yeah. I'm not going to do B. I'll do number D. Letter D. All right, so letter D, well, I can keep that part. In letter D, I still have 0.004 moles of acid to start with. But when I take this 0.021 times point...
No, wouldn't it be 0.0201?
Yeah, probably. All right, times it by 0.2, what do you get?
0.00402.
Yeah, well now this is going to be a base.
All right. Okay, so now we take this 0.00402, and you can still subtract it if you want, or really you always subtract the smaller from the bigger. So we would subtract this out, and we'd end up with 0.00002. And which one would you have excess? OH minus. Now that's just moles. So remember, you would have to divide that by the new total volume, which is 40.1 milliliters. So 0.041. 0.0401. I keep doing it wrong. Thank you. All right. And that would be your liters. So you divide these two numbers, and what do you get? Do you have that number, Smith?
4.987 times 10 to the negative 4. That's what I got.
1, 2, 3, 497.
Yeah. 987.
987.
Yeah.
Oh, for freak's
about
sakes. Okay, yeah, let's call it 5. All right, now that would be your molarity of OH minus. So this is where we have to add another step. So we now take the negative log of 0.0005, and that will give me what number? 3.3. But this was OH, so this answer is really my POH. So I got to take 14 and subtract 3.3 from it, and I get 10.7 as my pH. Jules? Oliva? Okay. They're sort of tricky, but they're not that bad. The problem with AP, and especially AP for the last, well, let's just say 6 months, every other day it's a new type of math. So which one do you use? That's where the issues are. I'm certainly aware of that. I don't have the ability to change that, though, because that's just how AP rolls. All right, for the next little bit, we need to talk about the curves that titration graphs give you. All right, we already talked about this one. Let's just talk through these 3 parts real quick. So titration graph, we basically chop into 3 parts. There's this one, there's this middle piece, and there's this. This is the titration curve when you have a strong acid and strong base. So we had a strong acid that we neutralized with strong base. We know wherever it ends high, that's the thing we were dumping into it. Whatever started low, that's the thing we were testing out. All right, so here, this stays relatively flat because even though you're adding OH minus here, still at this part, what is in excess from here to here? All right, the acid is in excess here. So even though you're adding OH minus, it really is reacting and just forming water, which doesn't change the pH drastically. Then we get to this part, and this part's important, and you should read it. It's this part right here, and it's called the equivalence point. I'm sure they're all there, just trust me, probably a dot required somewhere. That's the equivalence point, and that's where H plus is equal to OH minus. All right?
Where it's neutral.
Yep, that's where it's neutral. All right? Yeah, we'll call that green. Ooh. Doesn't look green, but whatever. All right, now, this middle part of this curve makes a drastic change in pH because in this area, the OH and H are almost equal. So as you add one or the other, now you are making a giant change in the concentration. And on this graph, it would be OH. Once all the acid is neutralized, then any OH you're adding is going straight in to increasing the pH. All right? But then it flattens out, and that's because we've overwhelmed the system, and we just have a nice and high concentration of OH minus. There's no more H plus being consumed, so it's just pretty much flat. All right? So you kind of have to be able to, you don't have to like write things, but just understand, like if it said the place on the graph where OH is being neutralized by H, that would be here. I don't know what they would be, but just kind of understand the 3 parts of the graph.
So it's like the acid in excess is begins the flattening a flat line at 2. Well, that OH in excess never go past 12.
No, you can get past 12. You just have to keep getting more. You can go up to 14. You just keep on adding more, and your concentration will increase. It's just not a drastic increase anymore. All right, this is going to say what I just said, probably in a better way. So from the start of the titration to near the equivalence point, the pH goes up slowly. just before and after the equivalence point, the pH increases rapidly. That's why it's so much steeper. And then at the equivalence point, the moles of acid equal the moles of base, and the solution contains only water and the salt from the cation of the base and the anion of the acid. So at neutral, we just have salt water.
So
All right.
Done that? Before you drink. Didn't they used to, but then a guy like died from it or something?
No, I don't know.
Mr. Bird told this guy that he drank it, but he had it wrong, and then he died.
That would be bad. I used to, my first couple of years I would drink, but it's just disgusting, because when you'd get done, you'd have warm salt water that tasted like cabbage juice.
Did it tie your, did it dye your mouth like?
No. It was fine. It just tasted disgusting. So I was like, why am I doing this? I don't have to. So anyway, but yeah, you can do it if you use the right indicator, but you do have to be careful. If you ever do an experiment like that, what you do is you take your beaker.
feed it to the dog first.
No. No. You just take a beaker that you know the beaker's water, and you add your indicator, and it turns a color. So this is your standard. You don't do anything to that. Then you take your beaker you're titrating it with, and if you do this, you'll be fine. And you titrate it until it's the exact same color as that, because then you know that it is exactly the pH of water. The only thing in there now is the salt. The only other thing in there is the indicator. And you shouldn't do this with just any indicator. It should be red cabbage juice, because that's actually a food. And as long you take a red cabbage and you like chop it up and then you boil it, it'll turn that water dark blue, and that water actually works as an acid-base indicator. We have some in our freezer. Anyway, as long as you make sure these are the same, then you're golden. If someone really died from this, which would surprise me, but if they did, they didn't have their standard to compare this to. And without standards, kids, we're lost in life. Okay, moving on.
So, I had a question.
All right, then, as more base is added, the pH again levels off, yada, yada, yada. All right,
Well, how much higher does the pH have to be to kill
depends on how much you drink.
0.1.
So one time I went to church and we, I don't know why I'm recording this story, but we put Drano in our sink. And Drano's like a 14. And we came back and our cat was dead. And our hypothesis is that because our sink was backed up, the cat got up there and like started drinking the water. And no moss. Dead. So if you get probably past 10, you're probably going to start hurting yourself pretty bad.
What is bleach?
Same, way up there, 14.
Yeah, why does it go to 14? Why can't
It
why
can
is
go
this-
higher. It's just most common things that we talk about don't go outside of that range. All right, so here we go. Now we have a titration of a weak acid and a strong base. You do have to be able to identify the curves, and I'm going to summarize these on a slide in a few minutes. There's two things. You have to identify that their curves are more gradual increase and then a steep increase, then a flat. So instead of flat up, flat, it now has a slope. Green's a terrible color to use right now, even though it's St. Patrick's Day. And then vertical, and then this.
Even the
Green
green should be the easiest color.
should be the easiest? What else? It's just not high contrast. Take that. All right, now, the other thing you need to know, and this is common sense, like even me at your age, I should say, I could figure this out. The pH at the equivalence point here should be greater than 7. And that's because you're adding something strong, a strong base, and a weak acid. So you would think it would make sense that you would end wherever the stronger thing is. Okay? And I shouldn't say end, but the equivalence point would be above 7 because you have a strong base and a weak acid. The next is just the reverse. Okay, well, there is math here. Ignore these. I hate this from our book. You would sort of do the same math we just barely did, except for you don't solve. If the excess is your acid here, it's a weak acid. And so a weak acid, we had to use Ka equals x squared over initial. And then we solve 4x and then plug that into negative log. So it's a little bit more complicated. These are uncommon. If they do titration math, it's almost always strong acid or strong base. Then if the weaker the acid, the more gradual, sorry, not gradual, the less flat it is, and there's hardly any change around the equivalence point. This is not a slide you have to memorize by any means. Just know the weaker it is, the less likely you are to use it in a titration. So it wouldn't show you much. All right? Then, if you now have a weak base and strong acid, we should end less than 7. And then you would choose methyl red because it changes under 7.
But if equivalent points equals is H plus equals OH minus, why wouldn't it be 7?
Why wouldn't it be 7? Because the weak base doesn't completely dissociate with the strong acid, just like the weak acid wouldn't completely dissociate and react with the strong base. Like it will, but it only does it after you pass the normal equivalence point. All right, and then this is a weird looking curve. It's a titration curve of a polyprotic acid. And that just means there's more than one H popping off. So we end up to have 2 in this one, or even 3. And you don't have to know anything about this besides that if you ever see a curve that looks like that, that's the titration curve for a polyprotic acid. Okay, so this next slide sums all these up and just the basics that you need to know about them. A few things. SA means strong acid. SB means strong base. WA means weak acid. WB, weak base. And then what do you think EQP means? Equivalence point. So this right here says equivalence point is 7 or greater, whatever, that's the plus sign. This means it's 7 or lower. And then like polyprotic acid, I mean that's not even one that exists, but they're just the ones that have a couple of bumps. So make sure and draw that out. The only question you have, you will ever most likely see, is just a multiple choice question that says this graph represents the titration of a blank with a blank.
So the only difference between the strong acid, strong base, and the weak acid, strong base is that there's the slope at the beginning.
Yep. That's the only way to tell them. Oh my, how are you?
Nice here. How's
It's just products.
It's just products. How come, Dewberry?
I don't understand.
It's because your reactant's a solid, and solids are not included. So if you were to write the KSP for this, you'd say KSP equals Ba plus 2 times SO4 minus 2, and that would be it. So it's the easiest because we don't have a denominator. I like math without dividing. Let me see where the next actual slide is. Oh. Yep, and KSP will always be that way. All right, the equilibrium constant expression for this equilibrium is Ba, we just said that, where the equilibrium constant is called the solubility product. Now, solubility means the ability to dissolve. And that's all we're doing. We're saying, all right, we're putting this in water. How does it break apart? And we will know how well it breaks apart based on the concentration of its ions. All right. The expression for a solubility product does involve stoichiometry, though. So if it's BaCl2 goes to Ba plus 2 and 2Cl minus, the equilibrium constant expression for this equilibrium is KSP equals Ba plus 2 times Cl minus squared. Whew, that was a good sneeze, though. All right, this square comes from what we've been doing forever, where the coefficient becomes the exponent. So when solving for the concentration of an ion, make sure to account. I hear noises, soccer players, and this annoyed me now. I've reached my limit. So in solving for the concentration of an ion, make sure to account for the subscripts in the formula. So if it's just easy, like Na and Cl, which we wouldn't do, but that's fine. It wouldn't go to Na plus Cl minus, or we're out of time, whatever, yada, yada, yada. We'll pick that up tomorrow. Please read this